Okay, let's get started. Good morning, everyone. Welcome back. We are fast approaching to the end of this semester, and I'm not quite sure whether we can finish chapter 7 and chapter 8 in this semester. But the important thing is, many important things are in chapter 6. So please pay attention to in this chapter. So chapter 6 is about power system operation, and as you know. So electricity markets rely on the power system infrastructure. So we have economics and the physical systems, and the participants do not have choice to use another system. So that's why we need to operate the system in a reliable way. And when outage happens, that is the customers are not quite happy because the outage cost is very huge. It depends on the types of customers. You may not be that unhappy, but the manufacturers, something like semiconductors manufacturers, will be very unhappy because turning on the system again costs a lot. So consumers obviously have expectations for continuity of the services. So when you enter your room, when you turn on your switch, you are expecting that the light will be on all the time. Okay. So avoiding outages requires an awareness of the whole system, not a part of system, but the whole system. So of course, when outage happens, if we cannot supply power for the whole entire system, a part of the system is cut off. So that is called a circular outage. And you may remember that in 2011 in Korea there was a circular outage because at the time I think that was September, and the temperature was unexpectedly high even though it was September. So there was a lot of load consumption for air conditioning, for example, and there was a power shortage. So the KPX decided to cut off some part of the load in the country, and that was circulating. And the minister of 산업통상자원부 resigned because of that accident. So maintaining the power system in a reliable way is very important. And the system operator is responsible for avoiding outages. So let's think about reliability. And electricity is public goods, and all participants benefit from it, benefit from reliability without subtracting from the reliability that others get. So this is good for everyone. So that's why we need to maintain the system reliability. And actually, when outage happens, the system operators is not liable for that, or does not have liability. Liability means 채무. Okay, and all the damages are on generators and customers, especially for the customers. So generators and customers need to bear the cost of outages. So the regulator need to set reliability standard so that the system operator can operate the system in a reliable way. So that is about planning standards and operating standards. So this planning means the planning of generation and the planning of the transmission network and the planning of reserve resources. Reserve resources. So what do I mean by reserve resources? They will be clear shortly. Okay, so what is the value of reliability? So why do we need to think about value of reliability? The reason is because to provide reliability to power system and the generators and consumers, it costs more, right? So the cost of outage is a function of the value that customers put on reliability. So if they expect this amount of cost will incur when outage happens, then that's the amount of the customers are willing to pay further. Okay, So you may remember the terminology value of lost load before, VOLL. So that concept comes in again. And the value of reliability depends on the duration of outage, several minutes to several hours or several days, and time of outage. And also it depends on the types of customers, residential customers, commercial customers, and industrial customers. Well, most residential customers are kind of okay, right? But commercial and industrial customers will be very unhappy. And the cost of outage is much, much greater to consumers than the producers. So from the generator's perspective, when outage happens, they cannot generate, so they cannot get revenue by generating powers. But the cost to the consumers is a lot higher than that. How much higher is it? 10 times, 100 times, or 1,000 times? Can you guess? Actually, a few hundreds times higher than the cost to the producers. Okay, so yeah, we have that figure here. So that is measured as the value of lost load, and the abbreviation for that is VOLL. So this is the value, the value that an average customers put on not consuming kilowatt hour or megawatt hour because of an unplanned outage. So this is measured dollar per kilowatt hour or dollar per megawatt hour. So typically, dollar per megawatt hour. And this VOLL is actually hard to determine because, how much damage would I expect when outage happens? How can we compute that? It's not easy. So the calculation of VOLL is based on survey, the survey from customers. Okay, so how much damage would you expect when outage happens? Samsung Semiconductors, Hyundai, or Kia Motors, etc. So, yeah, and this is a very rough calculation and grossly oversimplifies the issue. But anyway, this is useful information. So this is an example. Different countries and different regions. So United Kingdom, European Union, United States. MISO is a part of United States. New Zealand, Victoria, Australia, Ireland, Northeast USA. So VOLL measured as a dollar per megawatt hour. By the way, what is the typical energy price? Dollar per megawatt hour. The typical range, of course, it changes over time. S&P changes over time. But what is the order of dollar per megawatt hour? What is the price for electricity, electric energy? Roughly, $1 per megawatt hour, $10 per megawatt hour, or $100, $1,000 watt. Roughly speaking, $4. I was joking. Yeah, $100. Yeah. So in Korean, that is very similar to 101 per kilowatt hour, or $100 per megawatt hour. Order is like that. But here, this is a VOLL. If you remove 2 digits here, you can guess how much VOLL is higher than the normal energy price. So a few hundreds times higher than the normal energy price. Okay, so that's why we need to operate the power system in a reliable way. So, okay, 220, less than 100, very small, 400, yeah. So, the cost of reliability means we need to invest the facility so that we can avoid outage. So that's the topic of chapter 7 and 8, how to expand the generation capacity and how to expand transmission capacity so that we have enough generation capacity and enough transmission capacity to avoid outage. So that's about investment cost, the topic of chapter 7 and 8. And chapter 6 is about operating cost. Okay? So the cost of measures required to reduce the risk of outage. So to reduce the risk of outages, we may need to have more generators, right? And then let them be ready for contingent event that incurs additional cost, right? So that's the operating cost. And we have two methods, the preventive actions and corrective actions. The preventive actions means that before something bad happens, we ready for that, and that incurs cost. Corrective actions means that when contingency happens, we need to turn on a fast responsive generator, for example. So when something bad happens, we want to correct that. So that's called corrective actions. Okay. So system must be able to operate continuously if situation does not change. A very obvious statement. If nothing changes, the system must run regularly, but the system must also remain stable for common contingencies. These common contingencies means that the typically expected failures of the part of power systems, that is the breakdown of a power plant or a line cut of the transmission line. Okay, so you may remember that. Okay, we have this terminology, contingency. Okay, some kind of urgency, and when there are n components in power system like generators or transmission line, so sum of all the generators and transmission lines and transformers, well, the total number, let's say that is n. Okay, then because when there are n elements in power system, and each of them has a probability of breakdown, right? But typically that probability is very small. So when two independent components break down, that probability is very, very low. Okay, so when we design a power system, we hope that this power system runs in a reliable way, even if something bad happens, and just assume that only one component breaks down. Okay, so when there are, so that is called n-1 contingency. Well, the terminology is slightly weird, but what it says is when there are n components and only one part breaks down, still the power system runs in a reliable way. Okay, so that means we should withstand this n-1 contingency. Okay, so what kind of contingency do we have? Fault on a transmission line or other components like transformers, generators, sudden failure of a generating unit, and the rapid change in load. So these are the examples of contingency. So system operators must consider consequences of contingencies. n-1 contingent event. So the first one is the preventive actions. Put the system in a state such that it will remain stable if a contingency does occur. So a contingency occurs. Okay, so this one assumes that only one part, one element breaks down. So, and actually, so the generators does not run at its full power. The reason is because the operator system less than its full capacity is kind of preventive actions. Do you see what I'm saying? So actually this is important in your life as well. Normally use your 80% of energy power to do something. so that when something bad happens, when something urgent event happens, you need to use your 20% of additional capacity capability to use. Okay? Just my personal opinion. Examples. Limit the commercial transactions that are allowed in bilateral markets. And market clearing based on OPF in a centralized market. Yeah, so these are examples of preventive actions. And the opposite concept is corrective actions. And corrective actions are taken only if a disturbance does occur. So, and the purpose of corrective actions is to limit the consequences of this disturbance. And to do that, we need resources that belong to market participants. So, okay, you know ISO, system operator. And in chapter 1, we talked about the power systems evolve from a vertically integrated system to what? A vertically integrated system, this is a monopoly case, but it evolves to a fully competitive market. We are in between. Okay, so to deal with these corrective actions, we can think of because the current power system is not entirely vertically integrated. The system operators does not have all the resources to manage the power systems. What I mean is sometimes they need to purchase, procure the resources to maintain the power system from the market participants. Okay, so there we have a concept of ancillary service. Well, this keyword may not be familiar to you, but please remember ancillary service. What is the Korean word of ancillary? Yeah, this means 보조. Okay, so in energy trading, we trade energy, the megawatt hour or kilowatt hour, but this ancillary service is not necessarily trading of energy. It is about trading the capacity. Of course, it can include the trading of energy, okay, but the capacity can be traded, even if that is not used for power system. Just for making it ready to enter into the power system, that's the capability of that resource. Do you see what I'm saying? So, yeah, ancillary service or reliability resources that must be purchased from the market participants by the system operator. So that means the system operator does not have all the resources to operate the power system in a reliable way. Sometimes it needs to get help from other market participants, and this service provided by these market participants is called ancillary service. Okay? So when this ancillary service is called, the ancillary service will deliver some energy. Okay? However, the capacity to deliver is another important factor. Okay? So anyway, we need to balance the generation and load, so the energy need to be delivered. But from power system operator's perspective, the capacity is also important. Even if I do not use the capacity at this moment, but knowing that I have enough capacity is important. Okay? So the capacity to deliver is another important factors. And so, enumeration, the compensation, the money is paid back to the market participants who provided ancillary services based on availability, not energy delivery. So that's the difference. Okay? By delivering energy, you can get money. That's obvious. That is called energy trading. But in this ancillary service, this capacity, the availability, by providing this availability, you can get paid, even if you do not provide any energy. that can be, your generator can be used or may not be used, but anyway you can get money by providing the availability of your generation capacity. Okay? So based on megawatt, not megawatt hour. So how much reliability do we need? And how much cost, or how much is the VOLL? So the marginal value of reliability is same to marginal cost of reliability. So when outage happens, how much does it damage you? Is the value of reliability, right? So the cost and the value are equal. But the thing is, estimating this marginal cost of reliability, or VOLL, is very hard. It's not easy. So finding this equilibrium is very difficult. It requires probabilistic calculation, and there are a vast number of possible outages, etc. So anyway, our major concern is the cascading outage, not just a single outage, but a cascading outage. The cascading outage means one outage makes another outage. Okay? So because of this cascading outage, Northeast blackout happened in 2003, 20 years ago. Okay? So that's the starting point of the discussion about smart grid. Okay? So how to deal with an outage depends on the state of the system. Yeah, the state of the system means what is the voltage, what is the current, what is the frequency, etc. And and reliability resources can be used for various purposes. And so, ideal case, but in practice, deterministic rules defined by the regulator is used. And in essence, the regulator buys reliability on behalf of all the consumers. All the damages costs are on consumers, but on behalf of them, the regulators buys the reliability resources. And so we want to define credible outages. The credible outage means this one. Okay, one outage is a breakdown of a single element is okay. We design the power system like that. So the outages, the credible outage means that the outage that the system should be able to withstand without load disconnections. Okay, so typically outage of a single component and simultaneous outage of two components is assumed to have a very low probability. Of course, it may happen, but with very, very low probability. So preparing the system for N-2 contingency costs a lot higher than preparing the system for N-1 contingency. Okay? So far, this is acceptable. Okay, so system operator is required to consider only these credible outages. So to do that, the system operator needs to buy reliability resources. Procure, buy, same thing, but procure means 조달. Okay, so 조달청, 창살, 철창살은, procure means that. And okay, when to buy, that's the issue. And so it is about, we have in chapter 2, we discussed the market in terms of time, and there was a time called gate closure. So before gate closes, no energy transaction can happen. But after that, no further transaction is allowed, but the power system operator now need to get ready to inject some power from generator, etc. Okay, so there is a time called lead time. The lead time means from the gate closure to the time when the execution happens. Okay, so if this lead time is very long, it gives more time to the system operator to be prepared for the system operation. But if this lead time is too much, it increases the uncertainty, the forecasting uncertainty, etc. So we want to make it shorter, but then there is another uncertainty of the price. We have a trade-off between the price, how can I say, so uncertainty. And this is the moment when all the actions happens. And this is, let's say this is a gate closure. And this is a lead time. If you purchase something very, very early, that means the cost can be low. That's the purpose of a future market or a forward market. Okay, so if you buy something in earlier than you need, the price can be low, but uncertainty becomes high, and vice versa. If you buy the reliability resource at the last moment, then that moment and the time when something happens is very close, so there is small uncertainty, but the price at this time can be very high. Okay, so we have a trade-off between this price and uncertainty. Anyway, so long-term contracts for ancillary service means it reduces risk, but the price can be low, but uncertainty is high. The amount available not linked to the state of the system. And in short-term market, it is more closely linked to the needs, but increased risk of not having enough resources. So Chapter 6 is about describe the needs for ancillary services. So Chapter 6 is actually about ancillary services. Another name of Chapter 6 is ancillary service for reliable power system operation. And so we want to keep the generation and load in balance and keep the security of the transmission network. And how can we obtain ancillary services? Means how much ancillary services do we need, and how should these services be obtained? How should pay for these services? Okay, and the market participants can sell these ancillary services to maximize the profits from selling the capacity. Okay, any questions?
그러면 저번에 말씀드렸던 그 제너레이터가 에너지 마트로 굳이 참여 안 해도 돈을 벌 수 있다는 게 저 앤셀러리 서비스인 건가요?
Yes. Energy, so precisely speaking, even though not participate in energy trading, even if it does not deliver any megawatt hour, still it can get money by preparing its generator in a standby mode. That can provide some capacity for some duration of time. Okay, that is called availability. Yeah, you can get paid by providing availability, not energy. Okay, operational issues. Impact of failure. Suppose that we have two generators and each of them has 100 megawatt generation capacity, and then the maximum load that they can reliably supply together is 100 megawatt, 200 megawatt, but we are saying the maximum load that they can reliably supply together is 100 megawatt. Because of this, when one generator breaks down, still we can provide 100 megawatt. Okay? And for simplicity, let's first assume that all generators and generators and loads, and tie lines. This tie lines means the line between two different power systems, like Bolduria and Sylvania. Okay, tie, connect, yeah, tie lines. But here, just for simplicity, all the generators, loads, and the interchanges between the two systems that is connected by tie line. So that is called the amount of energy exchanged between these two power systems connected by tie line is called interchanges. So anyway, these three are connected to a single bus. Then only system variables are total generation, total load, and net interchange with other systems. Yeah, so this is about balancing issue. So if the production and consumptions are equal, the frequency does not change. It remains constant, 60 hertz in Korea, in the United States, and 50 hertz in Europe. Okay? But in practice, we have constant fluctuations in load and inaccurate control of the generators and sudden outage of generators and interconnections. So, and if load increases rapidly, then that may drop the frequencies, or excess generation can cause an increase in the frequencies. So, and you need to understand that the generators are designed to operate in a very narrow frequency range. The reason is because generator, what is generator? Turbine, you saw that before. It changes the mechanical energy to electrical energy, right? So the generator has a turbine and it rotates. It has a rotor, okay? So this is a mechanical system. And if the frequency deviates from its nominal range, that gives a lot of stress to this rotor. So this rotor can break down. Okay? So to protect the generator, if the frequency is too high or too low, then the generator is designed to leave from the system. Okay? I don't want to participate anymore, so I can leave. Bye. Okay, so the protection system of the generator disconnects the generators when the frequency is too high or too low. But the important thing is, when this happens, when there is an outage and the frequency is low, then one generator is decided to leave out of the system. Then we have further energy shortage. Then another generator can leave out of the system again and again and again. So that is called cascaded outage. Okay? So this causes further imbalance between load and generation. And this is the consequence of that. Northeast blackout in 2003. So 20 years ago. This is the United States. United States does not look like that. This part, blackout happened. Odeho, Michigan, blah, 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 Toronto. Anyway, this is a continent, not sea. Okay? So system operator must maintain the frequency within the limits. And so balancing production and consumption in energy. Then, okay, so the balancing is reflected in frequency, and if the frequency is at 60 hertz, that means generation and loads are balanced. But we are interested in the rate of change in frequency. When there is imbalance, frequency changes, but it can change rapidly or it can change slowly, and that depends on the inertia of the system. Okay, inertia. What is inertia? So what is the inertia of power system? So we have a generator, we have a load. Okay, we put energy here using fuel. Okay, and it makes steam, and this steam rotates this turbine, and this rotor and turbine has a mass, right? So it has a mechanical energy as well. So when it provides energy from this fuel, but it still has some mechanical energy. Okay, so when there is imbalance between this generation and loads, then this mechanical energy is translated into another electric energy. And if you have a lot mass rotor in the synchronous generators, then that means the system has big inertia because it has mechanical kinetic energy. So even if there is some imbalance between generation and load, still the system can sustain the kind of fluctuation. Do you see what I'm saying? So this mechanical kinetic energy can be thought of a buffer. Okay, and this inertia is big if the power system is big. So the inertia of United States power system is higher than the inertia of Korean power system because they have more generators and more buses, etc. But the thing is, because these days renewable generators kick in, and the inertia of the power system is getting smaller and smaller. Okay, so that means when some disturbance happens, the power system may not be able to withstand the kind of disturbance. Yeah, of course, these days people are talking about the virtual inertia using the power electronics technologies in PV and wind. But anyway, the synchronous generators has much higher inertia. So the frequency changes are much smaller in large interconnected system, the European power system or North America power system, than in a small isolated power systems like Korea. So load imbalance in an interconnected system causes a change in tie line flow. So yeah, inadvertent flow can happen when there is a breakdown, and these inadvertent flows can overload the tie line, and then there is another possibility that this line is sagged and touch the tree, and fire can happen, etc. So protection system may disconnect this line, and this could lead further imbalance between loads and generation. So each system must remain in balance. And what do I want to say here? Minor frequency deviations and inadvertent flows are not an immediate threat because if power system is big, it has some inertia. Okay, so that's why we have some time to prepare, and that's why initially the smart meter has a 15 minutes of sampling period. This 15 minutes reflects the inertia of the system. 15 years ago, we didn't have much renewable generations. We have mostly synchronous generators. So the power system has some inertia, so it can withstand 15 minutes, even if some imbalance happens. But now this time is getting shorter and shorter. Anyway, so this imbalance may weaken the system and must be corrected quickly so that the system can withstand further problems. So let's look at an example. This is a trading period, like 15 minutes or 1 hour. And we have 5 periods, and the load is hundreds of megawatt. The scale of this is like Jeju Island, roughly speaking. Okay, so the load changes like that. And for each time period, the energy is traded based on the forecasting, load forecasting. So this amount is traded, this amount is traded. Okay, and based on that, the energy is injected from the generators, right? Based on the contract, and this red line shows the actual generation, energy produced versus energy traded. But here, what you see is one generator has a problem, so it does not fulfill its requirement. So the generation is lower than the expected amount. So if we focus on the imbalance between this generation and the real load, there's the imbalance. So yeah, imbalance. So this is zero, balanced, but when this happens, we have a high imbalance like that. So when you look at this, when you look at this imbalance, of course there is a random fluctuation, and this random fluctuation comes from the randomness of the load. Or if we have a renewable generation, we also have this kind of random fluctuation in generation. And if you take the average, this is the slower load fluctuation, but this is from the outage of a generator. So the difference between load and energy traded, the trades do not track this rapid load fluctuation. The trade does not need to do that, and market just assumes load constant over trading period. And obviously, forecasting is always wrong, so there is an error. And so what about the differences between the energy traded and the energy produced? Imbalance happens, but these minor errors can be in control. And actually, where is it? The generators generator, they generate as they bid, and you may think they generate this constant rate, that constant rate based on the trading. But actually, that is true, but all the generators are connected to the system operator, and they are governed by the system operator. Okay, so we have a concept of governor. What is it, governor? So this governor controls the generators all the time. How can I say? So this governor adjusts the output power of the generators all the time by sending some signal. Okay, and that signal is called AGC, automatic gain control. Okay, so by applying this concept, the frequency can be regulated for that kind of small imbalance. For this kind of small imbalance, okay, you like the keyword fine tuning. Okay, so the controller of the power system, the system operator, the governor, fine tunes the output power of the generators using this AGC, automatic gain control signal. Okay, and so most of the generators are called governor controlled. How can I say? But the opposite concept of governor is that what is the opposite of governor? The opposite of governor is governor free. The opposite of governor is governor free. So what I'm saying is, actually we have different types of ancillary service resources like generators, but ESS also can be the resource for ancillary service. So the ESS, you can think of, okay, if you use ESS for frequency regulation, the purpose of ESS is to maintain the grid frequency at 60 Hertz. Okay? And then this ESS, there are two types of ESS. Governor-free ESS or how can I say? Yeah, governor-free ESS and the ESS that is governed by the operator. So the governor-free ESS means that it does not take any control message from the system operator, but it just senses local reason, and if the frequency drops, then it automatically reacts to that. So that is the meaning of governor-free. Even though I do not get any control, I can react to some event. Okay? Do you see what I'm saying? So the purpose of the advantage of ESS is that it is very fast responsive. If something bad happens, it can react less than 1 second, less than milliseconds, something like that. Other generators takes 5 minutes, 10 minutes, 15 minutes to increase the output power. But ESS is very responsive. So this is good for frequency regulation in a governor-free way. Okay. Yeah. Finite ramp rate at the end of the period. A unit outage creates a large imbalance. So different phenomena contribute to imbalances, and each phenomenon has a different time signature, and different services are required to handle this phenomenon. And exact definition differ from market to market about balancing services. So, okay, we are talking about ancillary service, and the terminologies are differ from market to market, but these terminologies are kind of okay. So the first one is regulation service. The second one is load following service. The third one is contingency reserve, and spinning reserve and non-spinning reserve. So let's go one by one. Okay. Yeah, regulation service. Actually, I already told you what regulation service is. This one, AGC. Okay. This is designed to handle rapid fluctuations in load, and so small unintended variations in generation. So regulation service is designed to maintain frequency close to nominal value, 60 Hertz, for example, and interchanges at desired values at the tie line. And the regulation service is provided by generating units that can adjust output quickly. The nuclear power plant cannot do this. Okay, LNG, coal-based power plant can do that, and they are connected to the grid, of course, obviously, and are equipped with a governor, and usually are on AGC, automatic gain control or generation control. Okay, so that is called regulation service, a type of ancillary service. Second type is called load following service, and this is designed to handle intra-period load fluctuations. This one, intra-period load fluctuations. So even though this is the contracted amount, still generators can follow the load. Okay. So that is called load following service. And it is designed to maintain, again, frequency close to nominal value and interchanges at tie line at desired values. And this load following services is provided by generating units that can respond at a sufficient rate. It needs to respond fast. Okay? But when contingency happens, for example, one generator breaks down, then must handle large deficits caused by outages of generators or tie lines. So to do that, to provide contingency reserve, first we have concept spinning reserve. What is spinning? This is spinning. So reserve is spinning. Our reliability resource is actually running, spinning, so that it can quickly enter into the system when contingency happens. So mechanically, we have this kind of one type of spinning reserve is the flying wheel. Wheel is flying. So it has kinetic, mechanical energy, but when it is connected to the grid, it can immediately supply electricity. So fast response time. So the spinning reserve, the primary response is quick but not sustainable. So when you think about this ancillary service, you need to think about three things. The first one is the response time. And the second one is what? Withstanding time. How long can it sustain? Okay. Of course, quick response and long withstanding time is good, right? And third one is the amount of energy that it can deliver. The power. Actually, yeah, the withstanding time, this is time, so yeah, power would be better. The capacity. So how much I can deliver, how long I can deliver, and how quickly I can get into the system. There are three key components for this ancillary service. So this primary resources immediately enter into the system to stop the decline in frequency. So it sustains just 30 seconds, something like that. And then the second response is slower, but it is more sustainable, like 30 minutes. Okay? And restore frequency to nominal value. And another types of reserve is non-spinning reserve. It takes much longer time, much longer response time, because like 10 to 15 minutes to come online, and they are designed to replace the spinning reserve. They can only sustain a short duration of time. So this is a very interesting example, and this is not an artificial example. This is what happened before. So on August 15, 1995, some of you were not born. Right? So on August 15, 1999, 12:25, 30-second, this time, more than 1 gigawatt of generation was suddenly disconnected from the power system of Great Britain. So this figure comes from National Grid, UK. Okay, so 1,220 megawatt, more than one nuclear power plant. That amount of generation was disconnected from the power system. So when that happened, this is a minute 25, 26, 27, this is 30 seconds. Okay? The frequency immediately drops. How much? 0.5 hertz, almost 0.5 hertz. This is a huge frequency drop. Okay? You know, in Korea, the KPX aims to manage the frequency within plus minus 0.2 hertz. Okay? So to prevent the entire power system breakdown, the primary resource is immediately connected to the power system. So actually at that time the system had a total installed capacity 65 gigawatt, but does not have AC interconnections with the European continent. So isolated system in that sense. So yeah, the primary response react within 10 seconds and is sustained for 20 seconds. And then the secondary response kicked in and it sustains for 3, 4, 5 minutes. And then gas turbines is now can operate and can provide enough energy power to the system. So the purpose of using this primary response and secondary response is because each reliability resources, ancillary resources have different response time, different withstanding time, and different capacity. Okay? Interesting figure. So classification of balancing service. So we are keep talking about balancing service, generation and load, using ancillary service. So regulation and load following services requires almost continuous action, but the amount is small, and they are within some range. So in that sense, this is predictable, and this is called preventive security action. And the reserve services, so regulation service, load following service, contingency reserve services. This is reserve services. Reserve services, the use is unpredictable because we don't know when outage happens. We don't know when the breakdown happens. So use is unpredictable, and these resources will kick in when something bad happens. So this is corrective security actions. But provision of this reserve is a form of preventive security action. And then also the definition and parameters depends on the market and the system. Okay. So do you clearly see the difference in regulation, load following services versus reserve service? This is for contingency, a breakdown of power system, a breakdown of a generator or something like that. Okay, but regulation and load following happens all the time. Fine tuning happens all the time. And maybe last slide of today. So effect of stochastic generation. Because these days we have a lot of wind power and photovoltaic generation, but the output can be very different from our forecasting. So this figure shows the estimate of the wind forecasting error and the required reserve when 26 gigawatt of installed wind generation in UK. Okay, so 26 of renewable generation is huge. You see that? So the estimate of wind forecast error, so we do not have the wind forecast error here, but this lead time is another indirect measure of the forecasting error. If this lead time is lead time is long, that means we can, there will be a huge forecasting error, right? And in that case, the maximum change observed, that means we need to have this amount of resource, is that 26 gigawatt, and this is 7 to 9 gigawatt. If lead time is just 30 minutes, still 1 to 1.5 gigawatt of reserve is required because of uncertainty. Okay, so that's why your forecasting is important for reliable power system operation. Any questions so far?
애초에 전력망을 설계할 때 플러스 마이너스 1Hz까지 버틸 수 있게 하면은 안 되나요?
Good question. I don't know. Plus or minus 1 hertz is too big. Okay, and I think in that case, there is a threshold, and just from personal experience, 1 hertz is way too big, and that is the acceptable range is 0.2. If the deviation is more than 0.2, then we have higher chance to have blackout. Actually, 0.5 still we can withstand that, but when we operate the power system, the KPX try to keep the frequency within this plus minus 0.2 hertz. Okay, and so the reliability of Korea power system is very higher than United States. Actually, the first reason, they are good. K power system is good. Second, relatively the Korea power system is new compared to the country where the power system was invented. That was invented 100 years ago. So some of the transmission lines, some of the generators are very old in that country. Okay. Any other questions? K power system. Sounds good. Okay, then I will see you on Wednesday. Thank you.